Okay. So we consider the equation x double prime plus pt to x equals to 0. So our idea is to study the oscillation properties of the solution. That means how many zeros that the solution of this function can have, but without actually solving the problem. Without actually solving the problem. So we say the first definition is we say that a solution is oscillatory. Okay. If it has infinitely many zeros in any positive interval. Okay. So a solution x is oscillatory if xt has infinitely many solutions. Many zeros, infinitely many zeros in any positive interval. So let me write t to infinity for any t, for all t. Okay. And and the equation star is called oscillatory equation. We call the equation star oscillatory if it has an oscillatory solution. So if it has an oscillatory solution, then we say that the equation is an oscillatory equation. Okay. So whether it has one solution or it has many solutions, that will be clear after I prove this theorem, because the second order equation will have two linearly independent solutions. So if it has one oscillatory solution, it will have other solutions are also oscillatory. This is what we are going to prove now. Okay, so the theorem is suppose you have x1 and x2 are two linearly independent solutions of this star. Okay. And A and B are two consecutive zeros of these are the two consecutive zeros of x1. Okay, with the order A less than B. Okay, then so you can write this as a let. Then x2 has at least one zero. At least 1 0 in open interval AB. The open interval AB. That means you have this is the point A and this is B, and these are the two consecutive zeros of x1. So let me assume that x1 is positive. So this is x1, two consecutive zeros of x1. Okay, then we say that within this there will be at least one zero of x1. Okay, so there will be at least 1 0 of x1. So let's see how this assertion can be proved. So this tells us that this equation star, if it has one oscillatory solution, then the second solution is also an oscillator, because between any two zeros of one solution there is at least 1 0 of the other solution. So if one solution is oscillatory, other solutions are also oscillatory. Okay, therefore an equation is an oscillatory equation if it has solutions, or if it's all solutions of this equation are oscillatory. Okay. So first thing is that to see that sorry, this is x1. This is x1, two consecutive zeros of x1. So we assume that x2 solution, and we know that x2 at the point A is non-zero. Also, x2 at the point B is non-zero. Why is that? If there are two solutions, linearly independent solutions, we know that the Wronskian is either completely zero or it is never zero. So if otherwise, okay, so you already have the condition that x1 at A is zero and x2 at B is zero. Okay, so why is this? Why you have this? This is because Wronskian of x1, x2 is non-zero. Wronskian is going to be non-zero everywhere. Therefore, x2 at the point A cannot be zero, and x2 at the point B cannot be zero. Okay. So what we have to show is x2 has at least one zero in the AB. So suppose it doesn't have any zero. Suppose okay, x2 is non-zero, the interval AB. That means it is either positive or negative. So again, without loss of generality, we assume that it is going to be positive. Okay, that is without loss of generality. Let x2 be positive in the interval A. So we have x2 is also like this. If x2 is also like this, then what happens? Okay, because x2 cannot be zero at the end points, therefore it has to be completely, you can write even the closed interval. x2 is positive in the closed interval A. So let us assume this, that this x1 is positive and x2 is also positive. Then let us take this function. Let ht be equals to x1 by x2. Okay, because x2 is the interval AB. Because x2 is positive, so this is well defined. x2 is strictly positive in AB, therefore ht is well defined. And also you see that h at A is 0 and h at B is 0. So once if I say that h at A is 0 and h at B is 0, then you should get an idea of what I'm going to use here. What is that? Rolle's theorem. So by Rolle's theorem, there exists a point C in AB such that h prime at the point C is 0. So what is h prime? H prime is nothing but x2 at C to x1 prime at C minus x1c into x2 at C upon x2 square. So this is 0. Okay, since x2 is not 0, therefore the top one, that is the nothing but Wronskian of x1, x2, the point C is 0. That is Wronskian of this point is, at this point is 0. But that is not possible, right? Because x1 and x2 are linearly independent. Therefore, this is a contradiction. Therefore, x2 has a 0 in A. Okay, and this is we are saying at least 1 0. Okay, but you can show that there is exactly 1 0. Okay. So it can be exactly 1 0. Why it becomes exactly 1 0? Now we showed that there is at least 1 0. It becomes exactly 1 0. So it is because if it has two zeros, I can interchange the roles of
Find one another.
exactly 1 0. If there are two zeros, and T1, T2 belongs to the interval A, then change the role of x1, x2. Change the roles of x1 and x2. Then what you should have is between two, because there are two zeros of x2, there should be at least 1 0 lying between of x1 in T1, T2. That's not possible, right?
Yes,
so by
hypothesis.
above, there exists at least 1 0 of x1 in T1, T2. But we assume that AB are consecutive zeros of x1, x2. So this is again a contradiction. Therefore, between any two zeros of one solution, there is exactly 1 0 of the other solution. So this is known as Sturm's oscillation theory. Okay, and if it has one solution, then it has. If it has one oscillatory solution, then all solutions are going to be oscillatory. So our aim is to, as I said, to study the eigenvalue problems. Therefore, we need to understand how these zeros depend on the coefficients of the equation. So how the zeros depend on the coefficients. Zeros of solutions depend on the given data. Because we are not exactly able to solve many of the eigenvalue problems, only of course it is a constant coefficients equation, we can solve it, or otherwise some special equations which has the solutions, especially we know the, for example, Legendre equation and Bessel equations, this kind of equations you can solve, but generally you won't be able to solve. So therefore we need to understand this, these are called qualitative properties. Okay, these are called the qualitative properties. So we need to understand the qualitative properties of solutions without solving them. So what I did just now is that I didn't solve any problem. I only, from the given equation and from the knowledge of our differential equations, we could say that if there are two zeros of one solution, there will be at least 1 0 of another solution. So how these zeros of the function depend on the data. What is the data here? We have very simple equations, that is x double prime plus pt into x is 0. So the data is only pt. So how the zeros depend on pt? So for example, let us take, say for example, let us consider the equation x double prime plus k square x equals to 0. We know that the solutions of this equation are sine kt, okay, and cos kt. These are the two solutions. Okay. So if you take, for say, k equals to 1, you have sine t and cos t. And when k equals to 2, it is going to be sine 2t and cos 2t. Now you compare the number of zeros of sine t and sine 2t. Okay. In, say, for example, 0 to 2 pi. 0 to 2 pi. So if I see from 0 to 2 pi, how many times the sine vanishes? Sine vanishes at 0. At pi by 2, it is going to be 1. And at pi, it is going to be 0. Right? At pi, it is going to be 0. And it goes like this, right? So this is 2 pi. This is the sine. Then how the sine 2 looks like? Sine 2 pi. Sine 2t looks like. At t equals to 0, it is again going to be 0. But at pi by 4, it is going to be 1. And at pi by 2, right? At pi by 2, at pi by 2, it will have 0, right? So this is pi by 2. So we'll have a 0 here, right? Again, one more 0 here, like this. That means in the interval 0 to 2 pi, the sine 2t has more zeros. Okay, it has 3 zeros. And similarly for the cos t. So when you increase the k here, the number of zeros are increasing. That means this kind of thing should happen even for the function. For a constant is what is happening. And if you have a function and if the solution is oscillatory, then for the larger coefficients here, the functions which are larger, then the oscillations are more. So this is the next theorem. It says the following. So this is called Sturm's comparison theorem. So this is the Sturm's comparison theorem. So it says x double prime plus p t into ax equals to 0, and y double prime plus qt to y equals to 0. Call this as 2 and this is 3. Suppose xt is a solution of 1.2 with the consecutive zeros at a and b. Okay, suppose x has consecutive zeros a and b. Okay, x equals to q, but they are not identically equals to q. Okay, it can be some points, it can be equal, but the functions are not identical functions. Okay, these are continuous functions in the interval. Okay, so if third one, y is any other solution, y has a 0, oh, sorry, y is any other solution, any solution of 3 is such that y at a is 0, then there exists a point in the interval AB such that y at c is 0. Q larger than P. If Q is larger than P, then the equation y, the solution y has between two consecutive zeros. That means that as I increase the coefficient, the number of zeros are increasing. Okay. The number of zeros are increasing. So P and Q, there are positions. Little later that they have to be positive, otherwise this will not be satisfied. So I don't require to put the condition that P and Q are positive, because we are assuming that X has two consecutive zeros. So I will tell you
Sir, your screen is paused.
Screen is paused?
Yes, sir.
Okay, let me share once again. Is it visible now?
No, sir. Yes, sir, no visible.
Now it is visible, right?
Yes, sir.
Okay. Right. So how do we prove this? So like earlier we assume let us say pictorially, the A and B are two consecutive zeros of X. Therefore, we assume that X is positive. You can assume X to be negative, but all the calculations will be the same, even if X is negative. So this is my X, and Y is Y also has A. At A it is 0, and something like this. Okay, something like this. Actually, assume that by contradiction, this is false. Okay. Assume by contradiction. Yt is positive in control A. Okay. Also, we know that xt is positive, right? Also, without loss of generality, we assume that xt is positive. Okay. So you have the two equations, that is x double prime. I said x double prime plus px into pt into x, and y double prime plus qt into y. So you multiply this equation, cross multiply, and x. Track these two equations. Cross multiply and subtract.
Sir, your voice is breaking.
X double prime.
Sir, your voice is not clear. It is breaking.
I will switch my network to okay. I'm not able to find where this hotspot. Okay. Do you have a mobile hotspot? Can you share? Okay, so can you hear me?
Yes.
So
Starting.
yes, yes.
जो प्रूफ है ना स्टार्ट से बता दो एक बार क्योंकि आपकी वॉइस सही नहीं आ रही थी.
Okay, so assume by contradiction that yt is going to be positive in the interval AB. We are already given that xt is a and b are the two consecutive zeros of x. Therefore, we assume that x is positive in the interval AB. That is without loss of generality. You can assume even the x to be negative. That doesn't make any difference. Okay, so once we have this, then you cross multiply these equations and subtract. Then we get this y into x double prime minus x into y double prime, okay, plus p minus q into x into y equals to 0. Now you integrate by parts. By parts in AB. So we get the integral of y into x double prime is going to be, okay, y into x prime, the interval AB at the end points minus integral of x prime y prime. Similarly, we will have the x into y double prime, the integral AB is going to be xy prime AB minus integral x prime y. So if you see that this integral x prime y prime will get cancelled because there is a minus sign between these two. Okay, therefore these two gets cancelled when I subtract. So what will be left is only the boundary terms. These are the boundary terms, and p minus q into xy will be there. Therefore, we get x into y prime, okay, minus y x prime. This is the boundary terms, the value of the boundary. This is going to be equal to the integral a to b q minus p, okay, into xt yt. Okay, and if you see what is this, because just substitute what is x and y. X is going to be 0 at both endpoints a and b. Therefore, this is going to be 0. Okay, so this term is 0. And this term at y at a is 0. Therefore, this is also going to be 0 at y at a. Therefore, this is going to be y at b into x prime at b. Okay, so this is equals to this. This is equals to this. So this is going to be integral a to b of q minus p into x into y into dt. Now you see how the graph of this, how these functions look like. This is ab, and x is like this, and y is like this. So if you see what is x prime at b, x prime at b is a decreasing function because it is coming from positive to 0. So x prime is going to be negative at the point b. Okay, and y at b is positive. So you have y at b is positive, and x prime at b is less than or equals to 0. Therefore, this product yb into x prime b is going to be less than or equals to 0. And now you see that q minus p. We assume that q is greater than p, greater than or equals to p, but they are not identical. Therefore, q minus p is greater than or equals to 0. And when you integrate a to b, and x and y are positive, these two functions are positive. Therefore, this is going to be positive. Okay, q is greater than or equals to p, and q is not identically equals to p. X positive, y positive implies the integral a to b q minus p into xy is positive. So this is not possible, right? So this is a contradiction. Okay, because the left hand side is non-positive and the right hand side is strictly positive. So this cannot happen. So therefore, as the coefficients become larger and larger, as the coefficients become larger and larger, the number of zeros of the function solution increases. Okay, so that is the theme of this Stone's comparison.
Left hand side is also positive.
Right? What is that?
Left hand side is also positive, sir. We can't get contradiction there.
Left hand side, y it is positive, y at b is positive, and x prime at b is negative, right?
Yes, sir, but we have negative sign.
Where?
X y prime minus y x prime.
Right,
then
but
this
that's what I said. You substitute the values of a and b, right? When you substitute the values of a and b, x into y, x is going to be 0 at both ends, and y is 0 at a. Maybe I did.
Yes, sir. There is sign, negative sign.
Yeah, I no, it won't come because I probably did not write it. When I copied from here to here, I changed one sign. Okay, so this is p minus q, and this is y into x prime minus, right? So yx prime minus xy prime. So this is yx prime. So this comes with this. See that this is what it is. Y into x prime. Okay.
Now, okay,
Y into x prime minus x into y prime. That's what we have. And p minus q, when it goes to the other side, becomes q minus p. Yeah. Okay. So let me do a problem here. I'll tell you what how this theorem can be used in even for some functions too. Okay. Look at the cos t and look at another function 2 sin t minus 3 cos t. Okay. Now I will say that this is take this as x and this is y. Between two zeros of cos t, there is at least one zero of y. Between two zeros of x, there exists at least one zero of y. Why is that? That is because x and y, these functions sin t, cos t, and they're all the solutions of x double prime plus x equals to 0. They're all solutions of, as both of them solutions are, both are solutions of this equation. Therefore, but otherwise to take a graph of this is, and in fact what we showed is that exactly there will be at least exactly one solution, 1 0. Okay, so another corollary. If L is the limit of t tends to infinity of qt and it is positive, it is L is positive, then x double prime plus qt into x, okay, equals to 0 is an oscillator. This is an oscillator equation. Why is that?
Trigonometric solution, I get one. We get trigonometric solution to solve this. That's why this becomes oscillator.
No, this is qt. Q is a function of t. Q is a function.
In the solution we get. In the solution we get the trigonometric function.
How you know that?
Let us suppose qt equals to 2 identically.
Qt equals to
2.
Qt equals to
2. 2 for whatever we want.
But that's not what is given, right? Qt is a function. Qt is not a constant, right? Qt is a function. If it is a constant, yes, we can write. If it is a constant, I can write the solutions. The whole idea is that only, right? For the constants, you can find exactly what the solutions are. And for qt is a function, you don't know whether you can find solutions exactly or not. You may not be able to find exact solutions. So that's what we are trying to do, that we are trying to compare, right? So that's the idea of this comparison theorem. The comparison theorem is that you take some q, okay? So if I want to compare, if I want to get some property of the solutions of P, the first equation 2, then I try to get a function, a q, which is greater than P, okay? Or if I want to get properties of the solution 3, then I try to get one function P, right? So that's what we are going to do. Constants. One of them can be taken as a constants. So that's what we are trying to do here. So since the limit is going to be L, okay, okay, so for large t, for some t, some big T, okay, what we will have is that qt, okay, So we take PT equals to L, okay. And because it is positive, we can always choose, the limit t tends to infinity is positive. So for all t greater than or equals to big T, this Qt is going to be greater than, say, L by 2. Okay, so Q2 is greater than going to be L by 2. So you take Qt, the PT as L by 2, okay, and Qt keep it as it is. Therefore, you have the comparison that PT is less than or equals to Qt. Okay, for T greater than or equals to big T. And then you apply the Sturm's comparison theorem. Okay, so every solution of Q has a zero between two zeros, two of equals to, yeah, right. So you have now the PT, Qt is greater than or equals to L. So therefore, by previous theorem, we compare the x double prime plus L by 2 into x is 0 and x double prime plus q into x is 0, y double prime. So now this says that between two zeros of x, there is at least one zero of y. And x has, it's a positive constant L. It's an equation with positive constant L. Therefore, x is oscillatory, therefore y is oscillatory. Okay. X is oscillatory implies y is oscillatory. Okay. Another corollary. So for oscillatory behavior, what is important? What is so this condition will give the oscillatory behavior. That is, if you have a coefficient where at t tends to infinity it is positive, then the equation is going to be an oscillatory equation. Okay, at infinity, it's enough to have at infinity. Okay, so if Pt is less than or equals to 0 and Pt is not identical equals to 0. Pt is not identical equals to 0. Then no solution of x double prime plus is oscillatory. Right? So the proof is easy. So take Pt as Pt and Qt as 0. Okay, so if I take Q to be 0, then if it has, suppose x has two solutions, x has two zeros. Okay, two zeros. Then y will have 1 0 between these two. And that's not possible because if I take Qt equals to 0, the solutions are going to be linear functions. So the linear function has 1 0 means that it is right. So between, if it is oscillatory, there will be many zeros, and the linear function cannot have that many zeros. Therefore, it is the equation is going to be not an oscillatory equation if Pt is less than or equals to 0. So that is why in the beginning I didn't say anything about the Pt. So those Pt's are non-negative. Okay, so I considered the equation of special time that is of this type of equation, but any second order equation can be converted into this. How do we convert? Take any equation, right? So this is the special type of equation we considered. So if we take any equation, if let us consider any general equation. Okay, so say x double prime plus pt into x prime equals to 0. Okay, and you take the transformation y, which is equals to xt into exponential of half integral of p. Then you will get that y satisfies an equation like this, y double prime. It is not difficult to check. You can check it easily. Half p prime into y equals to 0. So which is an equation of this type? Okay. So it is enough to study the equations of this type. It is enough to study the equations of this type. So they will have the same. If I can understand this equation, if I x double prime plus p x prime plus q x equals to 0, can be converted the solutions of this, and because this is multiplied by the exponential, as far as the zeros are concerned, x and y will have the same behavior because it is multiplied by an exponential function is not 0 anywhere. Okay, therefore the zeros of x and y are the same. Same means that the number of zeros will be the same, and in fact the zeros itself are the same. Okay, so this is about the oscillation theory. So now we'll use this oscillation theory in the next lecture to study the eigenvalue problems, to show basically that the eigenvalue problem has solutions, existence of eigenvalues for the highest term level eigenvalue problem. Okay, so do you have any questions?
Sir, what is this second term y double prime plus 2 minus p square by 4?
Yeah, so second term p square by 4 plus half p prime. P square by 4.
2 minus p square minus
Q minus p square by 4 plus half p prime. Anyway, I will share the notes in a couple of days.
Okay, sir.
Any more questions?